Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's the problem for today. Your company owns an asset which pays continuously at the rate of 10 minus $1,000 for t between 0 and 10, where t is time in years. The current market yield curve is flat with force of interest for all maturities equal to 5%. Find the Macaulay duration of this asset held by your company. And here's the solution. So the asset value in thousands of dollars is a function of the force of interest delta, which is equal to 5% in this case, is equal to this integral from 0 to 10 of 10 minus t e to the minus delta t dt. And its derivative with respect to the force of interest is the derivative of that integral. And of course we can just take the integral of the derivative, so that would be minus integral from 0 to 10 t times 10 minus t e to the minus delta t dt. Therefore the Macaulay duration equals the ratio of minus the derivative, so take out the minus in front of that integral and then it's just that integral, from 0 to 10 of t times 10 minus t e to the minus delta t dt, divided by the price, which is integral from 0 to 10 of 10 minus t e to the minus delta t dt. And the top integral can be split into difference of two integrals. The first one is 10 integrals from 0 to 10 of t times e to the minus delta t dt. And the second one is we subtract integral from 0 to 10 of t squared e to the minus delta t dt. And the bottom is a difference of 10 integrals from 0 to 10 of e to the minus delta t dt minus integral from 0 to 10 of t times e to the minus delta t dt. Now, we're actually given that delta is equal to 0.05, so we plug that in, and we have 10 times integral from 0 to 10 of t times e to the minus 0.05 t dt minus integral from 0 to 10 of t squared e to the minus 0.05 t dt divided by 10 times integral from 0 to 10 of e to the minus 0.05 t dt minus integral from 0 to 10 of t times e to the minus 0.05 t dt. And then at the top we note that this is the 10 times integral from 0 to 10 of t times the differential of e to the minus 0.05 t over minus negative 0.05. And the second thing the same way, minus integral from 0 to 10 t squared times that differential. At the top, at the bottom, sorry, we write the first integral as the integral from 0 to 10 of 1 over 20 e to the minus t over 20 dt, and then, of course, we need an extra 20 in front, so 20 times 10 is 200, minus integral from 0 to 10 t times the differential of e to the minus 0.05 t divided by negative 0.05 dt. This whole thing is effectively the same as we were taking a continuously weighted time to maturity, which is what Macaulay duration ends up being. We note that 1 over 20 e to the minus t over 20 is the density of an exponential random variable, say t, with mean 20, and therefore the integral from 0 to 10 of 1 over 20 e to the minus t over 20 dt is the probability that that kind of random variable is less than or equal to 10, which we know to be 1 minus e to the minus 1/2, because that's e to the minus 10 times 1 over 20. So 10 over 20 is 1/2. Also, as a result, then, the integral from 0 to 10 e to the minus t over 20 dt is 20 times 1 minus e to the minus 1/2, so approximately the number that you see there. Also, the integral from 0 to 10 of t times e to the minus 0.05 t dt, we do integration by parts, and this is, as I said, we had a differential of e to the minus 0.05 t over minus 0.05, negative 0.05. So we take u to be t and dv to be e to the minus 0.05 t. Then we have the product of u and v evaluated from 0 to 10, minus, so plus 1 over 1.05, the integral from 0 to 10 e to the minus 0.05 t dt, which we just evaluated a moment ago, so we use that value. And 1 over 0.05, of course, is 20, so 20 times 20 is 400. So the first expression is equal to minus 200 e to the minus 1/2. The second plus 400 times 1 minus e to the minus 1/2. So this is approximately, actually exactly 400 minus 600 e to the minus 1/2, and that's approximately 36.0816042. And then we do the same kind of integration by parts for integral from 0 to 10. This expression here, integral from 0 to 10 t squared times differential of e to the minus 0.05 t divided by negative 0.05, and we have u times v equal to t squared times the expression whose differential we have evaluated from 0 to 10, minus, so plus 2t times integral from 0 to 10 of 2t, which is the derivative of t squared, times e to the minus 0.05 over 0.05, the minus cancelled out with the minus that was in front of the integral. And that becomes negative 2000 e to the minus 1/2 plus integral from 0 to 10, 40 times t e to the minus 0.05 t dt. So that's negative 2000 e to the minus 1/2 plus 40 times 400 minus 600 e to the minus 1/2. That's approximately 230.202847. And the expression that we're calculating is effectively then 10 times the result of the first integration by parts calculation minus what we just calculated by second integration by parts over 10 times the integral from 0 to 10 e to the minus t over 20 dt, which we evaluated, minus the first integration by parts result, and that comes out to be approximately 3.06515501, which is answer B. Please remember that this is copyrighted material. The problem comes from me, and the solution is mine too. All rights reserved. Reproduction in whole or in part without express written permission from the author is strictly prohibited.